Alright folks, today we're going to be looking at finding some limits analytically. So let's though first start off with a review of what we've already done. Let's look at a few limits on this graph. So let's go ahead and say let's find the limit of f of x, and we're calling this function f of x. Let's find the limit of f of x as x approaches 4 from the left. And I'm going to write that limit of f of x as x approaches 4 from the left. That's what that minus means. It means from the left. So to find that limit, notice we're looking at the x value of 4. And as we approach it from the left like that, we follow our graph up. And we continue to go up, 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 up forever. The limit is infinity. Now let's look at the limit of f of x as x approaches 4 from the right. So this time from the positive side. So from the right, as I get closer that way, I follow my graph up, 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 also to positive infinity. That tells me that the limit of f of x as x approaches 4 exists and is infinity, since the left-handed limit is infinity and the right-handed limit is infinity. So let's look at this problem now. Limit of f of x as x approaches -2. Notice I don't say from the right or the left, so that means I have to check both and make sure they go to the same point. So x value of -2, from the left I'm going up to that point right there, and from the right I'm going to that same exact point, which has a y value of 3, so the limit is equal to 3. And let's look at this last limit here today. 3 of these limits right here that we're looking at, all at the x value of 1. But the first question says, what is the limit of f of x as x approaches 1? Well, to answer that question, we have to look at the two one-sided limits. So we need to find the limit of f of x as x approaches 1 from the right. So as we approach from the right, we're following that graph to that point right there, which has a y value of -1. If I find the left-handed limit, the limit of f of x as x approaches 1 from the left, I'm coming down that way to that point, which has a y value of +1. Since these two values, the left-handed and the right-handed limit, are different numbers, that tells me that the limit does not exist at 1. So let's go ahead and move forward. We're going to talk about a few basic properties of limits. So this is saying B and C are real numbers, so if you think about the limit as x goes to any real number, let's just pick one, let's say 5, of some number b, let's just say 2. Well, the limit of a number is just the number 2. That's because we're talking about, in this case, the horizontal line at the y value of 2, and if you think about the limit, it's talking about the y value at a specific x, as x gets super close to some value. Well, we're on a horizontal line, so your y value is always going to be 2. This one, very similar. This time, think about that x as the function y equals x. We know what that line looks like. As x gets bigger, y gets bigger. So if we have the limit as x goes to, let's use the same example, 5 of x, well, that's going to be 5. It's going to be whatever that limiting value is, because it's going to go straight to it, because it's a linear function with slope 1. And finally, the last one, following suit right there, limit as x goes to 5 of x to some power, let's just say 3, is that x value substituted in directly, 5 to the third, which is 125. Which leads us to where we need to be for today, limits of polynomial functions and limits of rational functions. So all this is saying is if you have some polynomial, let's call it p of x equals x squared plus 3x, it is saying if you find the limit of a polynomial at any point, again I'm just going to use 5, we'll keep using that x value, Limit of a polynomial at that point is just going to be p of that point, that function evaluated at that point. So that tells me I can directly substitute 5 in for my x's and get 5 squared plus 3 times 5, which is 25 plus 15, which is 40. Yay, math. Now the bottom part is just saying the same thing, but for a rational function. So like x squared plus 2 over x minus 1. If I want to find the limit as x goes to, well, anything but 1, because notice it says denominator cannot equal 0, and 1 would make the denominator 0. So let's go to 5. We can directly substitute in to that rational function. 5 squared plus 2 over 5 minus 1. 5 squared is 25, plus 2 is 27, over 5 minus 1 is 4. So now let's talk about our main strategy for finding the limits at holes. Well, we're going to patch the hole. And what I mean by that is we are going to pull the hole out of the function and find the limit of the simpler function. So again, it's all going to come down to factoring. So notice I'm rewriting my limit. I would like you to do the same. But now let's factor the numerator. X squared minus 16 is a difference of squares. So it can factor as x minus 4 times x plus 4. My denominator is still x minus 4. Notice I have the same factor in the numerator and the denominator. That gives me a hole, and I can rewrite this as the simpler limit problem. Limit as x goes to 4 of x plus 4. I totally removed the hole from the problem, and now I can evaluate this polynomial instead. So just take that 4 value, plug it in, and I get 4 plus 4 equals 8. Same exact situation here. This time let's factor the numerator and let's factor the denominator. So again, numerator, another difference of squares. So I'm going to get x plus 2, x minus 2. Denominator, I've got x squared plus 5x plus 6, so that's going to factor as x plus 3 and x plus 2. So I get a hole, and I will rewrite this as the limit as x approaches negative 2 of the modified function x minus 2 over x plus 3. And now I can directly substitute in because it does not make my denominator equal to 0. So I can get negative 2 minus 2 over negative 2 plus 3, which gives me negative 4. So now let's look at this similar limit. Same function, so I'm going to keep my factorization from the previous page. All I did was copy and paste it right there. But this time, notice we're looking at the limit at negative 3. But let's think about that function. What happens at negative 3? Well, I'm going to get a vertical asymptote. So sometimes your best bet is to just sketch a quick graph. So I know I have an asymptote at negative 3. I know I have a 0 at positive 2. Let's just check a point real quick. I'm going to check the point 0. So 0 minus 2 is negative. 0 plus 3 is positive. So at 0, I'm negative. That tells me I have to be down like that. I've got a horizontal asymptote at 1 going over. So I'm up like that. And I could have used that to figure out where I was also. Multiple ways to do this. So now I can easily see that the limit from the left is positive infinity as I follow my graph up, and the limit from, whoa, sorry, I just did that problem. That was positive infinity. And the limit from the right as I approach negative 3 is negative infinity. So again, that tells me that the limit as x approaches negative 3 does not exist. Alright, we want to do the same thing on this problem. Only thing is we have a difference of cubes in the numerator, and we don't necessarily know how to factor that. But think about what value we're looking at, 3. Something interesting is happening there. We want to figure out what. So let's go ahead and take that numerator, x cubed minus 27, and divide it by x minus 3. Quickest way to do that is to use synthetic division. So I take the solution of my divisor, which is 3, and I divide into my polynomial x cubed plus 0x squared plus 0x minus 27. Don't forget those zeros. Drop down the 1. I get 3. Whoa, that's totally not how it works. I get 1. Then I get 1 times 3 is 3. 0 plus 3 is 3. 3 times 3 is 9. 0 plus 9 is 9. And 3 times 9 is 27. So I get a remainder of 0. But, more importantly, this tells me that I have the limit as x approaches 3 of the function x minus 3, because I just divided by x minus 3, and I got x squared plus 3x plus 9, and that's all divided by x minus 3. So again, I get a whole, and so I can now answer this limit question. Limit as x goes to 3 of x squared plus 3x plus 9. And now I can directly substitute it in to get 3 squared plus 3 times 3 plus 9, which is 27. Last problem of the day. Again, we're just going to sketch a quick graph. So first off, think absolute value x over x is the mother function, so I know it looks like that somehow. But I do see that it's being multiplied by 2, which tells me my branches are at negative 2 and positive 2. And I also see that I have a minus 4 with my x's, so my graph is shifted to the right 4. So let's go 1, 2, 3, 4, 1, 2, 1, 2, and get this graph quickly sketched in there. And now I can easily see that the limit from the right is positive 2, because I'm on that upper branch. The limit from the left is negative 2, and the limit as x approaches 4 does not exist because I'm going to different y values. Done.